Wildlife poaching is a serious issue threatening key species populations. In this video, we would like to introduce Paws, the Protection Assistant for Wildlife Security. This is broadcasted from the Team Core Research Group at the University of Southern California. Do you know how many tigers are left on the planet? Today, there are about only 3,200 tigers left, 1/20th of the population 100 years ago. In addition, 3 out of 9 tiger subspecies are already extinct. Poaching is considered a major drive in tigers' population drop. Under the threat of poaching, the population of many key species is declining at an alarming rate. Such species declines can destroy ecosystems and economies that depend on them. To combat poaching, we bring advanced artificial intelligence technologies into the battlefield. Collaborating with researchers and conservation practitioners from different organizations, we developed Paws, a game-theoretic decision aid to optimize patrolling effort and suppress poaching. Paws automatically generates randomized patrol routes to target poaching activities. Paws is motivated by a trip to the Murchison Fall National Park in Uganda. Elephants, giraffes, hippos, and Uganda cobs are residents here. However, their lives are threatened by poachers, many of whom place traps and snares on the ground to poach wildlife.
This is the all these new methods of poaching. Wow, look at these traps.
Officers told us that more than 1,000 snares are found in the area every year. How can artificial intelligence help save the wildlife? There are multiple answers, and we focus on helping the law enforcement agencies get the most out of their patrols. One main challenge here is that the patrolling resources are limited when considering the vast areas in need of protection, so patrols need to be carefully planned. Therefore, we built Paws, which efficiently uses existing data to design randomized, proactive patrol strategies, optimize resource allocation, and increase wildlife protection. How does Paws work? In short, Paws takes basic information about the protected area and information about previous patrolling and poaching activities and uses a sophisticated algorithm to generate patrol routes. As the patrollers execute the patrol routes, more poaching data is collected and Paws will update the result. Now, what's inside this black box? The core algorithm weaves together learning, game-theoretic reasoning, and route planning. One key part of Paws is to learn poachers' behavior model. Based on the animal distribution information of the protected area, we analyze how the patrol frequency would impact the poacher's behavior. For example, with higher patrol frequency in these areas, poachers tend to circumvent patrols by placing snares in other areas. We build a mathematical model called SUQR to explain the poacher's behavior and learn the parameters of the model from real-world data. We further enhance our model through conducting human subject experiments. We designed a ranger-poacher game abstracting the real-world problem. And we had human subjects as well as domain experts playing the game. With a learned model, we are able to find the poaching activity hotspots, and more importantly, we can predict how those hotspots change if a different patrol strategy is deployed. This enables the game-theoretic reasoning. That is, in designing the patrol strategy, we not only want to hit the current poaching hotspots, but we also need to consider how would the poachers react and adapt to the new patrol strategy. We use computational game theory to complete this complex task. Computational game theory has been applied for optimizing limited security resources in multiple domains, with several applications successfully deployed in the real world to protect critical infrastructure, such as ports and flights. Another key part of Paws' algorithm is to deal with complex terrain on the ground. Our team went out for trial patrols in areas in Southeast Asia to better understand that topographical information is critically important in designing patrol routes. Paws builds a virtual street map from the topographical information. With this street map, Paws is able to plan detailed patrol routes that are compatible with the terrain. Integrating poachers' behavior model, game-theoretic reasoning, and route planning, Paws generates efficient patrol routes for wildlife protection. Paws has been tested in Queen Elizabeth National Park in Uganda and is in regular deployment in a conservation site in Southeast Asia. During Paws patrols, multiple human activity signs are found. We look forward to collaborating with different organizations to deploy Paws at multiple sites. Paws is a tool that can help protect wildlife and preserve global biodiversity. AI-based solution holds promise for addressing additional facets of this issue, such as investigating and interfering with the trafficking of illegal wildlife products.